Now we're going to take a look at fluid resistance. Up to this point, we've ignored air resistance for the most part, and so now we're going to be able to consider that since we've been exploring forces. Any object going through a fluid experiences a resistive force against the motion, and so fluids being liquids and gases. For slow speeds, we have kV squared, or force equals kV. For higher speeds, k times v squared. The force is in newtons. K is the resistive constant, and how much the greater this constant is, the greater the amount of resistance there is. And v is the actual speed of the object. And so for slow speeds, we just multiply the resistive constant times v. For higher speeds, it's a matter of v squared. So if we consider a motion of a projectile, something like this, what we've assumed is no air resistance. But in real life, what's happening is, with air resistance, it's going to affect the motion in the x and the y. So if we consider a position graph, y and the position in the y and then x over here, this would be more realistic in terms of real life, depending on how much air resistance we have. Terminal speed is where air resistance gets greater with higher speed and then eventually will equal the weight of the object. And so air resistance and the weight, the force of gravity or the weight, is equal to the force of air resistance as the object goes down. So if we think about the equation for terminal speed, we know for the force of air resistance, multiply the coefficient times the speed of the object, and we know that if it's reaching terminal speed, the weight of the object will equal to the air resistance kV, and so we can maneuver or manipulate our equation so the velocity, the terminal speed or the terminal velocity, is equal to mg divided by k. And so pretty simple equation to use to evaluate this, but nevertheless important. So draw the graph for the acceleration, or draw the acceleration graph for this object in free fall. If you look at the graph here, it's velocity over time. In this case, we don't have a straight line here, so you're going to have to think through how to do this. So go ahead and draw out both graphs and do your best. Try to draw what's happening with the acceleration over time, and then you can check your answer. Okay, so what's happening initially starting out, right? If we look at it here, velocity over time, or speed really, the slope of this line, right? If we get the slope of this line, we would get, a decent number. The velocity is changing pretty rapidly over time here. And then as we get further and further, that slope gets less and less and less if we get the instantaneous slopes of each of these, all the way until the point where the velocity tapers off and it's pretty much almost a straight line. And when it is a straight line, it's reached terminal velocity, acceleration is 0 then. There's no more acceleration. So the force of air resistance based on the data given is force equals 0.653 times v. What is the terminal velocity for the 3 kilogram object? So go ahead and pause the clip and go ahead and solve for that. Okay, so we can set up our equation. We can figure out the terminal velocity should be 45.02 meters per second as the terminal velocity for this object based on this constant here, which we could get from our graphical data, which we would do, we can do in real life.